This is our final Math 241 research article presentation. The Tumbling Box, inspired by Professor Susan Jane Colley's paper, The Tumbling Box, published in the American Mathematical Monthly in January of 1987.
The problem that we will be investigating is the behavior of a book-shaped object when spun about different axes. First, we can consider the diagram on screen. We can draw its principal axes as shown and label them x, y, and z. Notice that the x and z axes are labeled as stable and the y-axis is labeled as unstable. This indicates that if you toss the object into the air, putting spin strictly about the x-axis or the z-axis, it will tumble in a stable fashion. However, if you do the same thing about the y-axis, the object will exhibit a wobble, spinning about multiple axes. This behavior is quite interesting due to its unexpectedness, and as intuitively, one might expect all three axes to exhibit the same stable behavior. In this project, we will show that this behavior can be mathematically predicted by representing this scenario using a 3D system of ordinary differential equations. We will now show a video to provide visual intuition regarding the problem.
Here we see rotation around the x-axis. Here we see rotation around the z. Notice how both the x and the z rotate stably. And then this is unstable rotation around the y. The rotating body is governed by this equation. The zero vector equals dl dt body plus omega cross L. In the next few slides, we're going to try to build some intuition and motivate this equation because it's where our system of ODEs is derived from. If I gave you a mass and I said it moved from the position on the left to the position on the right, and I asked you to draw a vector representing its movement, you would draw something like this. It exhibits linear motion from left to right, and so you draw an arrow from left to right. If I asked you to do the same thing with this spinning disk, you would pick different points on the disk and draw vectors and realize that they disagree with each other. Per convention, because of this issue, we draw the vector representing angular momentum as the vector perpendicular to the plane of rotation. This is our vector L. Now consider a person standing on the rotating disk, unaware that they're rotating, but just looking at the vector L. They would see the vector L as rotating. This is dl dt body. However, we know that because of an assumption the model makes, that there's no external torque, that the L vector is not actually changing. This truth is seen by an outside observer. In order to remedy these two perspectives, the equation introduces a correction term for the phantom movement that the person on the disk sees. So dl dt space is the zero vector, dl dt body is the perspective of the person on the disk, and omega is the angular momentum. That phantom term is W cross L. Because it's not actually moving, we have the zero vector, the perspective of our person on the disk, and then the correction term. And this is the equation that governs the rotating body. Rearranging, we find that dl dt body is equal to L cross omega. And this is the starting place for our derivation of our system of ODEs.
From this equation, we can derive a system of three ODEs. Our state variable is L, which is a vector whose components represent the angular momentum about the x-axis, y-axis, and z-axis. A parameter for this system is I sub j, which represents the moment of inertia about the x-axis, y-axis, and z-axis. This model makes a couple of assumptions, namely that we're dealing with a uniform box with distinct dimensions. This means that the box we're considering can be imagined to look something like a book, or like a phone, as we saw earlier. This model also assumes that no external torque is applied to our tumbling box, as mentioned earlier. From these assumptions, we can reach this inequality about our moments of inertia, which is that I1 is greater than I2, which is greater than I3, which is greater than 0.
Thinking about what trajectories might look like, we can use the fact that dl dt space is equal to the 0 vector. This implies that the magnitude of L is unchanging, or is equal to some constant vector c. Because L is a 3-tuple, we're working in a 3-dimensional plane, which implies that trajectories lie on a sphere. To reason about what trajectories might look like beyond what's presented in the paper, we used Mathematica's ND-solve in order to generate trajectories for this system of ODEs. Here's a sample trajectory for initial conditions L1 equal to 0.35, L2 equal to 0.5, and L3 also equal to 0.5. We note that this is for t equals 0 to t equals 15. Here's another angle, and you can kind of see how this travels along the bottom half of a sphere. And here's another angle. Here's a bird's eye view. We begin our analysis of the system of ODEs by finding the equilibria. To find these, we need L1 prime equal to L2 prime equal to L3 prime equal to 0. By inspection, we find that we have equilibria at plus or minus 1, 0, 0, 0 plus or minus 1, 0, and 0, 0 plus or minus 1.
Once we found the equilibria, we used linearization to estimate the behavior of the system at each of the 6 equilibria. We achieved this by calculating the Jacobian for the system and then plugging in the 6 equilibrium points, yielding a linear system of differential equations for each point. The origin behavior of those systems provide an approximation of the corresponding equilibrium behavior in the nonlinear system. The linearized systems are shown on screen, with the positive variance resulting from the positive equilibrium value and the negative variance resulting from the negative equilibrium values.
The next step of our linearization is to find the Jacobian matrices at each equilibrium point. When we calculate these, we notice that each is a 3x3 matrix, but each also has a row of zeros and a column of zeros. We can eliminate this constant row and column, and we're left with 2x2 matrices for our Jacobians, which are seen on the slide. From these 2x2 matrices, we used Mathematica to figure out the eigenvalues near each equilibrium point. Now we're going to recall our inequality with our moments of inertia. I1 greater than I2 greater than I3 greater than 0. So now that we know the eigenvalues, we're going to use them to draw some conclusions about our equilibria. So near plus or minus 1, 0, 0, we notice that we have 2 purely imaginary eigenvalues. At 0, plus or minus 1, 0, we have 1 real negative and 1 real positive eigenvalue. And near 0, 0, plus or minus 1, we have 2 purely imaginary eigenvalues. So we know that 1 real negative and 1 real positive eigenvalue correspond to a saddle point. And we also know that purely imaginary eigenvalues correspond to centers. But for now, the best we can actually say is that the equilibrium points at plus or minus 1, 0, 0 and 0, 0 plus or minus 1 are possible centers. We'll say more about this later. Based on our linearization, this is what we think our phase sphere might look like. Notice we have a saddle point at 0 plus or minus 1, 0, and we also have possible centers at plus or minus 1, 0, 0, and 0, 0 plus or minus.
Although the linearized system indicates there to be centers about the L1 and L3 axes, we need to ask the question of whether there are actually centers in the nonlinear system. This is because the Hartman-Grobman theorem indicates that if we find purely imaginary eigenvalues in a linearized system, which should indicate a center, that doesn't necessarily mean that the equilibrium of interest in the corresponding nonlinear system is a center. We can investigate whether the L1 and L3 equilibria are actually centers by manipulating the ODE. It can be proven algebraically that the 2 equations on screen follow from the original 3 equations. And the reason we want the equilibria to be in this form is that they can be integrated to yield the equation of a cylinder, the significance of which we will explain shortly. We can integrate these manipulated equations by considering this fact, which is that the derivative of the square of some L component is equal to 2 times the product of that L component and its derivative. Using this fact, we can proceed from this blue equation, which was highlighted in orange on the previous slide, to this purple equation by simply making a substitution according to the fact we just established. We can see that the purple equation can be easily integrated due to the integral and derivative canceling out, yielding the equation at the bottom after some simplification.
So what does this prove? First, the orange equation here is the same as the orange equation here. This purple equation can be derived from this purple equation in the same way that this first equation can be. They're both equations of cylinders, with radiuses C1 and C2 respectively. They lie on the x and the z axes. When these cylinders intersect with the sphere, they create trajectories that lie on a circle, with radius C1 and C2 respectively. As we make C1 and C2 arbitrarily small, the radii of these circles gets arbitrarily small as well. In other words, trajectories that start arbitrarily close to these equilibria will stay there as they lie on a circle. This proves that these are stable centers.
We also took a different approach to investigate the L3 equilibrium at positive 1 using Mathematica. We achieved this by using ND-solve to visualize the trajectories of solutions to the system. We plugged 4 initial conditions into ND-solve, each of which lay on a point on the sphere successively closer to the equilibrium. We confirmed algebraically that each of the conditions L1, L2, L3 that we selected satisfied the equation L1 squared plus L2 squared plus L3 squared equals 1. Notice in this first plot, we see a trajectory that encircles the L3 axis. It is far from the L3 equilibrium point vertically and also has a relatively large radius. However, as we move the initial condition closer to the equilibrium point, the radius shrinks as well. Notice that visually, this final trajectory appears to have completely converged on the equilibrium point.
The real-world interpretation of our research presentation and Colley's paper is that a body with distinct dimensions, uniform weight distribution, and no external torque being applied to it will rotate stably around its longest and shortest axes, but unstably around its middlest length. In the case of the phone, it will rotate unstably around the y-axis, or the axis on which the charging port lies. Further research could include bodies that have no distinct dimensions, such as a cube, different shapes, like tetrahedrons, or bodies like a sphere. It could also include bodies that don't have uniform weight distribution.
We'd like to thank our Professor Kate Meyer for providing us with wisdom and guidance along the way. And we would also like to thank Carl M. Bender and Stephen A. Orsag for writing their very helpful advanced mathematical methods for scientists and engineers.